In the previous two videos, I introduced you to Monte Carlo methods as a means of looking at the characteristics of statistics and statistical hypotheses test. In the next two videos, we're going to still look at Monte Carlo methods, but this time more focused on using them for non-parametric statistics. That is, we are now approaching a very practical application or applications for Monte Carlo methods as applied in a non-parametric statistical framework. In this video, I want to look at Monte Carlo to estimate local relative efficiencies. Local relative efficiencies are more useful to us in a study framework than asymptotic relative efficiencies. Let's remember some of the points that I've made in the past about these two methods, as well as perhaps adding a few more points. Asymptotic relative efficiency is mathematically derived. That's the positive nature of asymptotic relative efficiency, is that they have been theoretically proved. However, that theoretical proof is asymptotic, as the name implies. It's based upon very large sample size, actually as the sample size goes towards infinity, and very small effect sizes as the effect size goes towards zero. They're useful for helping us get a general sense of how methods compare to one another, but it can be quite different than what we actually find in practical research settings where we're not going to have that big of a sample size and we may have a larger effect size. Local relative efficiency is study dependent. It depends upon a particular sample size and it depends upon the anticipated effect size. This is why we're not going to see mathematical proofs for local relative efficiency, because there's an infinite number of local relative efficiencies, whereas for any two statistical test and any single distribution, there's only one possible outcome for asymptotic relative efficiency. Local relative efficiency depends upon your particular setup for your particular study. So we're not going to mathematically derive local relative efficiencies. But the nice thing is now with Monte Carlo methods, as you've discovered, is we don't need to mathematically derive, we can do it empirically. Asymptotic relative efficiency and local relative efficiency have factors in common. Both of them compare two statistical methods. For example, we might compare the Wilcoxon signed ranks test to the t-test. And both are based on a specified form for the population distribution. For example, we may make this comparison assuming an underlying distribution that's normal, or we may make a separate comparison assuming an underlying distribution that's a logistic distribution, and so on. So these are factors that are in common to both of these, but LRE is more practical as a means to make study decisions if we can calculate it, and Monte Carlo methods are the path to calculating LRE. Now, even though we may use mathematical distributions to calculate our local relative efficiencies, and maybe our underlying population distribution doesn't adhere to a mathematical form, we can look at the properties of a mathematical distribution. For instance, if we have an underlying population distribution form that is platykurtic, that is light tails, we could use a uniform distribution as a mathematical model, not that it matches up our actual distribution, but rather that it is getting close to a mathematical formulation of that actual distribution, even though it's not a perfect match. Similarly, for heavy tails, we might look at the Laplace distribution. So we're not looking here at mathematical models of strictly fitting over, superimposing over our population distribution, but rather looking at the properties of those mathematical models and seeing if we can match some of those up to our actual population distributions. Of course, seldom do we know the actual population distribution, so it makes sense that we're just thinking in broader terms like, do I anticipate I'm going to have heavy tails in my distribution because of the particular measure I have and the participants that are in my study? Do I anticipate I am going to have lighter tails in my distribution? Do I anticipate I'll have a skewed distribution, and so forth? So let's see how we can use Monte Carlo methods in order to estimate local relative efficiencies. I'm calling up here an R notebook, and let's work through this. Although we know the asymptotic relative efficiency for many nonparametric and parametric test comparisons, as I've discussed, ARE is based upon some situations that are probably unrealistic in our studies. We're probably not going to have close to an infinite sample size. I bet you're not going to have that. And we're probably not going to have very small effect sizes. I have the wrong word here. I'm going to change it right as we're speaking. ARE is based on very large sample sizes and very small effect sizes. Our study may use smaller sample sizes or reveal larger effect sizes. Thus, it would be helpful to know the LRE. I'm going to use throughout this notebook the coin package, which provides excellent functions for some exact nonparametric methods, including the ones I've looked at in past videos that are based upon one sample, either a randomization test or a permutation test. So I'm going to use that coin package with this Monte Carlo LRE exploration. Specifically, in this video, I'm going to look at the local relative efficiency of Fisher's test with original scores compared to the t-test, so an exact method compared to a parametric method that is based on the normal distribution. And I'm going to look at the local relative efficiency of the Wilcoxon signed ranks test compared to the t-test. I'm going to use a uniform population distribution. That is a platykurtic distribution. Now, interestingly, we know that the ARE is 1 for both of these exact tests when compared to the t-test. So that means if you have a very, very large sample size and a very tiny effect size, we should have about the same rate of rejection, the same power for both the t-test as we would for the Fisher exact test and for the t-test as we would the Wilcoxon signed ranks test. All three of that would have about the same power in that particular situation. But our question's going to be about making these comparisons with smaller, more realistic sample sizes and larger effect sizes. I want to begin by comparing the Fisher's test with original scores to the t-test. So I'm going to load the coin package. And now that it's loaded, in a previous video, I discussed the mean and standard deviation of the uniform distribution. And I'm going to use that information to calculate a standardized effect size. I'm assuming a match pair design and a population of difference scores ranging from negative 20 to 30. In raw terms, the treatment has shifted the distribution 5 points in the positive direction. So picture that. If you have a uniform distribution and if you have different scores between someone in a treatment that is matched to someone in a control, if there is no treatment effect, what do you expect the median of those different scores to be? You expect it to be 0. And so if you have a uniform distribution, you expect half of that distribution to be negative, half to be positive in a uniform fashion. That is a flat-topped platykurtic fashion. So our treatment has added 5 points to the individuals in the treatment condition. So it has shifted the distribution 5 points. So the median is now going to be at 5, and we're going to have 25 below the median, which takes us all the way to -20, and 25 above the median, which takes us to 30. So we've shifted the distribution 5 points above 0. So the null hypothesis is no longer true. Unlike the past Monte Carlo studies where we looked at type 1 error rates in the videos that I did previously, in this Monte Carlo study, we're really focusing more on power, or lowering our type 2 error. Now, using the formulas that I provided before for the mean and standard deviation of a uniform distribution, I'm putting in the minimum and maximum values into the formula for the mean and for the standard deviation. And notice what I'm going to do here. I am going to calculate a standardized effect. That is, I'm going to look at how much the mean has shifted, divided by the standard deviation. Let me do that. And over here in my environment window, I see that the raw shift, as I mentioned, was 5 points, and the standardized shift is about 0.3, or just over a third of a standard deviation. That would still be considered a substantial effect for most research in the behavioral, social, and medical sciences. I'm going to now draw 2,000 samples with a sample size of 15 match pair difference scores for each sample. Each time I'm going to conduct Fisher's exact randomization test and also the t-test. And what I'm going to do is I'm going to count how many times the exact test has a lower p-value than the t-test. That is, how many times did it exhibit more post hoc power, that is, after we've drawn the sample size, more post hoc power than the t-test. So a lower p-value would indicate a better chance of rejecting than a higher p-value. So let's track how many times Fisher's exact randomization test wins out, as it were, over the t-test. Now let's briefly look at this code. I have here 2,000 trials that I'm going to do. So I'm going to draw 2,000 samples. The sample size is going to be 15. This is going to be a counter, this NP more power, where I count how many times the nonparametric test had more power than the t-test. And I'm going to start that counter at 0, and then I'm going to add to it every time the nonparametric test wins. So I'm going to do this, all this code here, I'm going to run through 2,000 times, my number of trials times. I'm going to draw from a random uniform distribution. You remember from past videos that R unif indicates the function in R for a uniform distribution and randomly taking numbers from it. So I'm going to take n numbers, n is 15, and I'm setting the parameters of my uniform distribution as I discussed from -20 to 30. Now the reason that I'm rounding this to 4 digits is because if I leave all of the digits in there, the coin package exact test does not work. It will give you an error message that it cannot do anything with real values. There's too many decimal places. So I'm still going to leave quite a few decimal places. I'm going to leave 4 of them, but at least this will allow the method to work. So that's why I'm rounding. And so this will give me my original score. Now what I've done here on the next line is set up for the future. I've set it up so that I could use a replacement score instead of the original score, a replacement score like a rank or a normal score. But in this case, the replacement score is the original score because we're doing Fisher's test with original scores. So the replacement score is the same as the original score. Why did I do this? Again, so that I could just come and change this little bit of code if I want to use ranks or normal scores. And I can go ahead and do those and see those ranks and normal scores if I change that code. All right, the portion here below now this is all for the coin package test. This is all information that the symmetry test, which is the function I'm going to use from the coin package, the symmetry test needs. It needs my response variable to be set up in a certain format, and that's what this is doing. I'm not going to go into the details of what it's doing, but in short, it is going to create a 0 for whichever member of the pair did worse, and then it's going to use the difference between the pairs as the score. So it's going to actually create pairs of scores, even though I'm giving it a single difference score. If that difference score that I gave it was, say, 5, it's going to create a 5 and a 0, simply meaning that one member of the group, either the control or the treatment, is 5 above the other. What this next part does is it tells which member's in the treatment, which is in the control, and what this next part does is it blocks or matches. You may recall from your past statistics courses that a match pair design is the same as a block design with just 2 members in each block. So that's what that's doing. And so the real key here to this function is right here where we're looking at our scores as a function of what condition they're in, and we're blocking based upon that matched pair. The next line tells me that I'm going to do a upper tail test. I said alternative equals greater, and that I want an exact distribution. Now this is pretty remarkable that I want an exact distribution, because notice I have 15 in my sample size. So I'm going to go over here to my console and take 2 to the 15th power and recognize that this is actually going to have to create 32,768 different randomization possibilities, and it's doing it every time we run the test. And how many times are we going to run the test? We're going to run it 2,000 times. So it is actually going to do 32,768 randomizations 2,000 times. I'm glad that this coin package and my computer is doing this and not me. Once we have the symmetry results, we're going to do the t-test. That should be pretty quick and easy to do the t-test. And then here is where I'm actually going to compare to see if the p-value for the symmetry test is smaller than the t-test. And if so, I'm going to say the nonparametric test has more power. And then I'm going to take the proportion that the times the nonparametric test had more power by dividing by the number of trials, and by multiplying it by 100, I can then get the percentage. Okay, so that in a nutshell is what's going to be taking place, and I'm doing this exact test. This is probably going to take a while. I'm probably going to have a lot of dead air, but I'm going to cut it out. So I will see you on the other side of this test. Here goes. Okay, I was away for about 3 or 4 minutes while the computer did its work using the coin package to do an exact test, and we're ready to peek at the results. Here they are. 55% of the time, the Fisher's exact test turned out to be more powerful than the t-test. Now, if I was to do this over and over and over again, in other words, 2,000 more trials, 2,000 more trials, I think sometimes this is going to be a little bit under, sometimes it's going to be a little bit over 50, but it's going to hover right around 50%. Why is that? Because the Fisher exact test uses original scores. The t-test uses original scores. So I expect for local relative efficiency to be very similar to asymptotic relative efficiency. Asymptotic relative efficiency is 1, meaning that we should get about a 50-50 split in terms of which one does better. And the same thing is true here. I will tell you that I've tried this several times before making this video, and what I just told you does indeed happen, that sometimes it might be 48 and then 52 and 51. And if I were to increase the number of trials, say up to 10,000, then we could actually hone in on that 50%. But I'd also have to be needing to go away and take a walk for an hour or two and come back and get my results. And I just don't want to do that. So let's accept this result that Fisher's exact turned out to be more powerful 55% of the time. It's roughly going to be about 50% because we are still using original scores. You might say, well, why even bother with Fisher's exact test? Glad you asked. We don't expect the t-test will necessarily have the type 1 error control that we would anticipate. We don't expect that our actual alpha will be the same as our nominal alpha. So if I set a type 1 error rate of 5%, I may in fact end up with less or more than 5%. That would be a good Monte Carlo study for someone to conduct to see if you get less or more than 5% on the t-test with a uniform distribution. Whereas Fisher's exact test, we're going to get right close to 5%, especially since we have 15 observations. If we have less observations, then because of the discrete jumps, I might be a little bit away from 5%. But here, I'm going to be close to 5%. So Fisher's exact, we know, controls the type 1 error and gives us the same amount of power as the t-test. Good reason to consider Fisher's exact test in this situation. But can we do even better with perhaps something like ranks? So I'm going to repeat this. I'm doing the exact same code down here, but this time I'm using Wilcoxon's signed ranks method. So the only difference here is this line right here. On this line, I am setting my replacement score to be the signed ranks. Notice how I do that. I take the absolute value of the original score and rank them, and then I multiply it by the sign of the original score. So if the original score was negative, the associated rank, after ranking with absolute values, the associated rank will become negative. So that's the only thing I'm doing different. Everything else is the same. So let me go ahead and hit the run button, and I'll see you on the other side of this. Okay, I'm back. And here we are, 23.2. The Wilcoxon signed ranks method in this situation, when we had a sample size of 15 and a fairly substantial effect size of 1/3 of a standard deviation, came nowhere near 50% of the time. It was 23% of the time that it was most powerful. We know the asymptotic relative efficiency is 1 for a uniform distribution when comparing the Wilcoxon to the t-test. So what happened? Well, remember, that's asymptotic relative efficiency. We know it to be 1, not empirically, but mathematically. But that is very large sample sizes and very small effect sizes. So in the real world of research, if I have a uniform distribution, I'm probably not going to turn to the Wilcoxon signed ranks distribution for that platykurtic distribution. I'd rather use Fisher's exact test. Fisher's exact test has just as much power as the t-test, and it holds the type 1 error rate where the t-test may not. So I'm not going to use this here, but let's do one more investigation. The Wilcoxon signed ranks method did not fare very well because the LRE is quite different than the ARE in this situation. So let's see if I can mimic the ARE with larger sample sizes and smaller effect sizes. So I'm going to set the sample size to 500. That's still not infinity, but it's a much bigger sample size than the 15 we were using. And we want to have the effect size be very small. So look at what I've done here. I have created a different standardized effect. If I look over here in my environment window, that standardized effect is 0.03 standard deviations. Not even a tenth of a standard deviation, but 0.03 standard deviations. So using 0.03 standard deviations, let's go ahead, and a sample size of 500. I think we would all agree that's a pretty small effect. And for practical purposes, a pretty large sample size. Let's go ahead. We'd love to run this, but be careful. Look at how many different randomizations I'm going to have to do. 2 to the 500. That's 3 followed by 150 zeros or some number, but that's how big my number of randomizations is going to be. And so if I rely on my poor little coin package to do that, this could take me years to do. I'm not going to wait around that many years. I know that I can edit out the dead air, but I'm not going to edit out years worth of dead air. So here's what I've done. The coin package allows us to put in an approximate test. Now you might think that's a large sample approximation. It is not. It is not a large sample approximation. The coin package actually will give you a large sample approximation if you ask for it, and the key word for that is asymptotic. That will give you a large sample approximation. But when you put in approximate, what it's going to do is actually do sort of an exact test. Obviously, it can't be exactly exact, so it's going to do a pseudo-exact test and give you a very good approximation of exact values based upon Monte Carlo methods. And I told you that there were 2 videos that we were going to look at in which we studied Monte Carlo methods as applied to nonparametrics. That's my next one. In the next video, I'm going to show you how we can use Monte Carlo methods to give us a pseudo-exact value. In other words, we're doing here a Monte Carlo within a Monte Carlo. Okay, so by telling the coin package I want an approximate, I'm telling it, please give me a Monte Carlo exact value, exact in quotes, of course, and I'm doing a Monte Carlo simulation. So it's a Monte Carlo within a Monte Carlo. All right, there's my N of 500. Here's my smaller effect size. I'm going to hit the button, and I'll see you again on the other side of this. Okay, I'm back, and of all the times in which I had to edit out dead air, that was by far the longest. Here it is, 41.45. Before, when we had a larger effect size and smaller samples, it was 23% of the time the Wilcoxon did better, and here it's 41% of the time. In other words, the t-test is still doing better in terms of power. It's not necessarily doing better. Actually, I know it's not doing better in terms of the actual type 1 error rate, because the Wilcoxon is going to hold the type 1 error rate right near that 5% value. But the t-test may be suffering in terms of type 1 error rate. I don't know whether the type 1 error rate is being conservative, meaning that we're under our nominal level, or liberal, meaning we're above our nominal level, but in any case, it's probably not right at 0.05. But it certainly is providing more power. Now, I worry first and foremost about type 1 errors, but after that, I want power. So what about this asymptotic relative efficiency of 1? We are not there yet. We're not at the large enough sample size and small enough effect size to see this become 50%. So what this tells me is that in just about every practical situation, I will not want to do the Wilcoxon if I believe I've got a uniform, or perhaps even if I have a platykurtic, light-tailed distribution. In those cases, then I'm not going to turn to the Wilcoxon. I might turn to the Fisher exact, or, as I've said in a previous video, the normal scores method can yield more power for platykurtic distributions. I'm not going to show that to you here. I'll leave that to you to convince yourself that that is indeed the case. I think there's a point to be made here as we finish this video, and that is local relative efficiency studies are worth it. You might say, should I really take the time to investigate this? Well, if you know something about your distribution, and if you want to maintain your type 1 error rate, and if you want to find the method with the most power, yes. This only took us a relatively short amount of time compared to how long our total research study will take. So taking a little bit of time to do a Monte Carlo study to see which method is going to yield the most power and maintain type 1 error rate under the particular study conditions that you have and that you anticipate, I believe is well worth it. Why don't people do this very often? Well, many of them don't know about the nonparametric methods. Others don't know about Monte Carlo methods. Others don't know about local relative efficiencies. You know now about all three of those things, and so you can take advantage and seek methods that will provide you the most power while maintaining your type 1 error rate.